Okay, let me get this. All right, so this is our energy, work, and power study guide. All right, so how is potential energy defined, and what is our equation? So potential energy is our energy of position. And in our course, we're using gravitational potential energy. So it would be like the energy of position above a reference point, like the Earth. This is also, we refer to this as a stored energy. So this is like an energy waiting to convert into something else. And the equation we use, PE equals mass times G. G is our acceleration due to gravity, times h, and h is our height, again above a reference point. So it might be the Earth, but it might be like when we did our roller coasters, we had the table. Some of us had the table as our like zero height point. So it just depends on how you define your scenario. How is kinetic energy defined? This is our energy of motion. Okay, so you've got to be moving in order to have kinetic energy. And our equation for kinetic energy is 1/2 times mass times velocity squared. Okay. Total mechanical energy, that is the sum of our PE, our potential, and our kinetic. So how is it calculated? We just add those two up. But it's basically all of our mechanical energy, our energy due to position and motion of our object. Okay. What does conservation of energy mean? So this is a law that says energy can't be created or destroyed, just transformed. So energy can change from one type of energy to another, but we are never going to lose or gain energy. Energy is a conserved quantity. Let me write that over here. That means that our total energy of an object is going to stay the same. Conserved quantity. So for example, what happens to the mechanical energy of a book falling from a high shelf in terms of PE, KE, and total energy? So let's say we've got our book, it's up here on a shelf and it's going to fall down. Okay, so the book is going to have its highest PE while it's on the shelf. So it's at a height, it's not moving yet. Then the PE converts to KE, kinetic energy, as it falls. We have our highest kinetic energy at the bottom, right before it hits the floor or whatever. But then my mechanical energy is the same at all points. So I've said before in class, it's like you have a bucket, okay? You have a bucket and it's got a certain level of matter in it. That's your mechanical energy. You can't take anything out of the bucket. You can't add anything to the bucket. You've always got that same level of matter in the bucket. Within the bucket, what makes up that matter can change, like convert between kinetic, potential, back and forth. You might have all of one, you might have all of the other, you might have some of each, depending on where you're at. But that total is going to stay the same. If I throw a ball into the air and it gains 20 joules of potential energy as it travels upwards, how many joules of kinetic energy did it lose? So as the ball is traveling up, if it gains 20 joules of potential energy, it's going to lose the same 20 joules of kinetic. Okay, that kinetic is being converted into potential. What must be true of the total energy of the ball? It stays the same. Whatever value it has, it's going to be the same value. And I don't have enough information here to say what that value is. I just know that the total energy of the ball is a conserved quantity that's going to stay the same. Okay, rank from greatest to least. So the greatest, this is a roller coaster. My greatest potential energy is going to be here at point A, where I have my highest point. Okay. My greatest kinetic energy, it could be B or D. Okay, those two look like they might be about the same height, I guess. So I'll say it could be either one of those, but these are my low points. So kinetic and potential energy are inverse. When you have more potential, you're going to have less kinetic. When you have more kinetic, you're going to have less potential. And so we can see that in terms of the height difference here. Total mechanical energy, again, same at all points because energy is conserved. So A equals B equals C equals D equals E. We're going to have the same total energy at all these points. It's just going to be a different combination of potential and kinetic. Okay, frisbee flies through the air 2 meters off the ground and a speed of 4 meters per second. So this frisbee has got potential energy because it's at a height above the ground, and it has kinetic energy. It has some of each because it's moving. So it has both potential and kinetic energy. What's the total energy of the frisbee? Well, I can get that by using my two equations that we talked about up here to calculate for the frisbee. And I'm going to add those up. So I'm going to have my total mechanical energy of my frisbee equals potential plus kinetic. So I've got mgh plus 1/2 mv squared. So let's see, the mass is 0.5 times 9.8 times my height is 2 meters plus 1/2, again mass is 0.5 and the speed is 4 meters per second, and I'm going to square that. So need my trusty calculator. So my potential energy is 0.5 times 9.8 times 2 for 2 meters, 9.8, and that's joules, plus my kinetic energy is 0.5 times 0.5, so that's for my 1/2, and then my mass, and then my velocity is squared, so that's 4. So 9.8 plus 4 is 13.8 joules. So this frisbee, as it's flying through the air at a height of 2 meters, it's got a height, it's got speed, so it's got some of each type of energy. I just calculate those, add them up, and here's my total energy. Okay, I'll do one more. I'm not sure how long this video is because I didn't pay attention to when we started. Okay, so 2 identical rocks are dropped from the same height on Earth. Just before they are released, compare the potential energy of each rock. Oh, they're dropped from the same height on Earth and on Saturn. Okay, so on Earth, I'm going to have mass times g of 9.8, or here it says you can round it to 10, that's fine, times height. And then on Saturn, I'm going to have same mass because they're identical rocks, times 28. That's the acceleration due to gravity on Saturn, because Saturn's much larger than the Earth, in case you didn't know that. It's a really big planet. It's the second biggest planet. And then H is the same. It says drop from the same height. So my potential energy of my rock on Saturn is going to be much greater because it has a G value of 28. It's going to be almost 3 times greater than my rock that's dropped on Earth, because this G value is different. And we didn't really talk about that as much in class, but we have learned before that G is a quantity that changes if you are on a different planet because of different gravity. So that's what we see here. Okay. Okay, I'll stop this video here and continue with the next one.